In problems 8, 9, 10, and 11, we also want to use our transformations to graph these quickly. So if we have x plus 4 to the fifth, we know that we're going to have a saddle type of graph, and it's going to go through negative 4 on the x-axis. For number 9, we know that we have a x to the fifth again, so we're going to have another saddle graph. And since an x minus 3 is on the inside of the parentheses, we know that it will shift 3 to the right. And since it's plus 5, it will also be up 5. So our saddle will be going through the point 3, 5. We also know that this saddle is going to be a little bit steeper since there's a 2 out in front. So we just want to draw a slightly steeper saddle. For number 10, we have x to the sixth minus 3, and we know that x to the sixth looks like a very narrow parabola. And since we have a minus 3 in the back, we know that its vertex will be at 0, negative 3, and then we'll have a very narrow parabola going through that. For number 11, it might be easier to rewrite it as negative x plus 3 to the fourth plus 2. So now we know that we have, again, a narrow parabola, but since there's a negative out in front, it's going to be facing down. Since x plus 3 is on the inside, we're going to have a vertex at negative 3 and positive 2, but it will be facing down. For number 12 and 13, we want to write the right hand and left hand behavior. And since we have a negative coefficient and an odd degree, we know that the function will start up and end down. So it rises left and falls right. For number 13, we have a positive leading coefficient and an even degree, so we know that both ends will rise. So both left and right rise. In number 14, we want to graph the polynomial, but in order to do that, we need to find its zeros first. So first I'm going to factor out an x squared. So I have x squared minus x minus 2. And then I can factor more. So I have an x minus 2 and an x plus 1. So I know that I'll have zeros at x equals 0, x equals 2, and x equals negative 1. And since the x was squared, I know that x equals 0 will have a multiplicity of 2. So when I graph it, I want to put my x-intercepts on at negative 1, 0, and 2. I also want to check the end behavior. Since I have an even degree and it's positive, I know that both ends will end up. So it's going to go through negative 1, make a parabola at 0, and then come back around and go through x equals 2. For number 15, I'm going to factor out a negative x, and that will leave me with 2x squared plus x minus 1. And factoring that more, I have 2x and an x, and in order to get a positive 1 in the middle, I'm going to need a plus 1 here and a minus 1 here. So I know that I'll have zeros at x equals 0, x equals 1/2, and x equals negative 1. So I'm going to put those on my graph. And since I have an odd degree with a negative leading coefficient, I know my graph is going to start up and end down. And none of my zeros have a multiplicity, so it's just simply going to go through each of my zeros. In number 16, we want to verify that x minus 2 and x minus 5 are factors of the polynomial. So in order to do that, I can use synthetic division. And since it's x minus 2, I'm going to use a positive 2 on the outside of my synthetic division and fill in all of my coefficients.
Where's the flag? Where's the flag music?
So since we got a 0 for a remainder, we know that x minus 2 is a factor and 2 is a 0 of the polynomial. So then to check that x minus 5 is a factor, I'm just going to continue with my new coefficients and test 5. If it is a factor, it should work. And it does. So now I have 3 remaining numbers, and I'm going to turn that into a polynomial, x squared minus 4x plus 3. And to find my other two zeros, I'm going to factor it. So I get x minus 3, x minus 1. So I know that my complete factorization is going to be x minus 3, x minus 1, and my two originals, x minus 2 and x minus 5. And then my 4 zeros are going to be x equals 3, 1, 2, and 5. In number 17, we need to find the possible rational zeros, but we do not need to find the actual zeros. To find the possible zeros, we first need to list the factors of our constant, which is 6. So the factors of 6 are plus or minus 1, 2, 3, and 6. And then our factors of 10, our leading coefficient, are plus or minus 1, 2, 5, and 10. So now for our possible rational zeros, we need to put all the factors of 6 over all the factors of 10. So first we'll put them all over 1. So we have 1, 2, 3, and 6. Now we'll put them all over 2. And remember, you don't need to repeat. So we have 1/2, and then 2 over 2 is 1, so we don't need to write that. But we'll have 3 halves, and then 6 over 2 is 3, and we already have that, so we don't need to rewrite it. So now we'll put them all over 5. So we'll have 1/5, 2/5, 3/5, and 6/5. And then we will put them all over 10. So we have 1/10. 2 over 10 is 1/5, and we already have that, so we don't need to relist it. But we will have 3/10. And then 6/10 is 4/5, or I'm sorry, 3/5, and we already have that, so we don't have to relist it. In number 18, we're verifying that 8 is an upper bound of the polynomial and -4 is a lower bound, which means that they're not zeros, but if 8 is an upper bound, all the zeros will be smaller than 8, and if -4 is a lower bound, all the zeros will be bigger than -4. So if I use synthetic division with 8, I should get all positive numbers on the bottom in order for it to be an upper bound. And 8 times 74 is a really big number. It is 592, so we get 600. So since they are all positive, we know that 8 is an upper bound. So now we're going to do the same thing with -4. And if they alternate on the bottom, then we know that it is a lower bound. And they do. So we know that it is a lower bound because of alternating signs. Number 19, we want to use Descartes' rule of signs to determine the number of positive, negative, and imaginary solutions to this polynomial. So in order to determine the positive solutions, we want to first count the number of sign changes. So we see that there's 1, 2, 3 sign changes, which means that we can have either 3 or 1 because we always go down by 2 possible positive solutions. Now to find the negative solutions, we plug in a negative x, and we know that every coefficient that has an odd exponent will change signs. And everybody that has an even exponent will remain the same. So in this case, we see that there are 1, 2 sign changes, which could mean that there are 2 or 0 negative solutions. However, if one possible combination is 3 and 2, another possible combination is 3 and 0, and if one possible combination is 1 and 0, another possible combination is 1 and 2. So we need to write those down as well. To find the imaginary solutions, we see that the degree is 5, so there must be 5 total answers. So if we look at the first row, we already have 5 answers, so there can't be any imaginary solutions. In the second row, we see that there's only 1 solution, so there must be 4 imaginary solutions. There must be 2 if there are 3 positive, and if there's 1 positive and 2 negative, there must be 2 imaginary. For number 20, we want to match the equation of the parabola with the graph. So we know that this parabola has a vertex at 2, -1, so we must have an x minus 2 minus 1. And we also know that it's going down, so there must be a negative out in front, which means that it must be the answer C. In number 21, we want to write the equation in standard form. So the first thing I'm going to do is subtract 2 to the other side. And there's nothing out in front of the x squared, so we're ready to complete the square. So if I take -8 and divide by 2 and square it, I'm going to get 16. So I want to add 16 to both sides of the equation. So I have y minus 14, and I'm going to factor to get x minus 4 squared. And then my final answer, I'm going to move the 14 over to the other side. And I see that the answer is B. In number 22, we want to find the vertex of the parabola. So we can use the equation -b over 2a and plug it in, or we could put it in standard form. Either way works. I'm going to do x equals -b, so positive 4 over 2 times 1. So I know that the x value of my vertex is 2. So now I'm going to take 2 and plug it back in order to find the y part of my vertex. So I have 4 minus 8 plus 10. So I know that the y part of my vertex will be 6. So my vertex is 2, 6, C. In number 23, we want to find the x and the y intercepts to y equals x squared minus 5x plus 4. So to find the x intercepts, I'm going to factor. So I'm going to have an x minus 4, x minus 1. So my x intercepts will be 4 and 1. And then to find my y intercept, I'm going to plug in 0 and get y equals 4. So we have a lot of choices that look very similar, and we want to remember that if you have an x-intercept, the x comes first, so it's at 4, 0, and 1, 0. If you have a y-intercept, a 0 comes first. So that would be answer B. In number 24, we want to find a quadratic function that has a minimum point at 1, -2 and passes through the point 0, 0. So remember that if it has a minimum point, that is also a vertex. And we know that it must be facing up in order for that minimum point, or in order for the vertex to be the minimum point. So I can use y equals a times x minus h squared plus k and plug in my h and k. So I have a -1 and a -2. And then I can plug in the point 0, 0 in order to find my a value. So I get that 0 equals 1a, or just a minus 2. So my a value will equal 2. So my final answer will be y equals 2 times x minus 1 squared minus 2, which is choice A.